In this video, we're going to start looking at some things about vectors. And some of this you may have seen already in previous math class. But first thing, plotting vectors. Okay, so plotting the vectors 3, -1, and 4, 2. So let me just quickly give a rough sketch here. 3, -1 is a vector that will have a direction that goes over 3 and down 1. So this vector will look something like that. Okay. Vector 4, 2 will mean this vector will go over 4 units and up 2 units. So it will begin and do something like that. Now, where the vector starts really isn't important. It just needs to have that, over 4, up 2, or of course in the previous example, over 3, right 3, and down 1. Adding two vectors together. Geometrically, what this means is that you're combining. You're saying, well, I went right 3, and then I apparently went right 4 more when I added the two together for a total right movement of 7. And in the first vector, I went down 1, but then I went in the next motion up 2 for a total of 1 net unit up. Now, subtracting vectors. I sometimes like to think about subtracting vectors like you're saying 3 plus -4. It's like you said, I went over 3, but then I went back 4. I went the opposite of +4. You end up at -1. And then starting with a movement down 1, but then subtracting 2 more means you had a total movement down 3. Next, you see I have a scalar out front. So this scalar means that essentially you quadrupled your original motion. So now your motion is 12, -4. And in the second case, you doubled your original movement. So you have 8 and 4. And then apparently I'm adding these two things together. So a total of 20 and 0. Now the magnitude of the vector. On my sketch here, the magnitude means what is the length of this vector. So the vector had a length of 3 in the right and 1 down. So we use Pythagorean theorem to find the total length of the vector. So 3 squared plus 1 squared. So it is the square root of 10. And again, I'm going through this pretty quickly because I think you've seen this. You saw it in Calc BC after the AP exam. It talked about some vectors. All right, next. This is always kind of tricky for people, adding vectors when they have a picture. And here's how I would kind of approach this. I would think about it like, okay, you started with A, you did A, and then you add vector B at the end of it. You see vector B over here. So I'm sorry, I'm going to probably draw this a little bit small, just, because to save room. But you do vector A, and then at the end you add a vector B. So your total vector, my kind of answer vector, is in red. Okay, and that this is A plus B because you did A and then you did B. Okay. Next, A minus B. And again, I would think about this like it's A plus -B. It's like saying A and then the opposite of B. And the opposite of B is essentially 180-degree rotation. So it's like saying, okay, I did A. And then whereas before, B was kind of down like this, now I'm doing the opposite of that. I'm going this way. So the final A minus B vector is something like that. And the last one says you take A and you double it. So essentially you're doing A twice, and then you're doing B, and again, I'm sorry, I'm not quite drawing this to scale for the interest of room, but then you're doing B 3 times. So it's something like this. Now, one of the things that will come up, and I'll talk about a little bit on the next slide, is just this idea of a geometric representation. The geometry here is like saying if I add two vectors together, I do one, then I do the other. What's the resultant? The geometric representation of subtraction is saying I do one and then I do the opposite of the second. And of scalar, it's like I do the vector and then I do it again. All right? So what is a vector? A vector is something that has a direction and it has a magnitude or length. Okay? So we're typically given a vector, in 2 dimensions as something like that. 3 dimensions, of course, would have an extra, like a z part to it. But it's something that tells us in what, how much do we move in x, how much did we move in y, or z if you're in the 3rd dimension. And then we calculate the length of that by doing Pythagorean theorem or distance formula. Now, a couple of just naming things. Where the vector starts is called its tail, okay? And where it ends, or where you put the arrow, is called the head. Now, what does it mean if 2 vectors are equivalent to each other? Equivalent vectors means they could start at different spots, but they have to have the same direction and the same magnitude. Okay, so that means that in this, I apologize, I'm going to make a rough sketch here. If you had a vector that did something like this, and you had another vector that was, like that, and I hope they're at least close enough to the same that you can get the idea. Those 2 could be equivalent. Even though they don't start at the same place, they have the same direction, like the same components. Often we call those, we call these things like what happened in x and y, we call those components. They would have the same components and therefore the same magnitude. If 2 vectors have the same general direction but different magnitudes, we'd say that those are parallel. That's one of the ways we know something is parallel. All right, so a geometric representation of vector addition, we already talked about on the previous slide. Vectors, when they are added, you do one vector, then you do the other. The yellow there, it represents what is their representation. It connects the tail of the first vector to the head of the second vector. Whereas vector subtraction, I kind of put this over here, would do the first vector, but then, let's say the second vector was like this, it would actually turn that around and do the opposite of that vector. So the resultant vector would do this. So it's doing the first and then the opposite of the second. And finally, the representation of scalar is to do a vector over, as many times as scaled. So the resultant vector is from the tail of the initial starting spot to the head of the last vector.